Is it fine now? Are we audible? But I can see the computer over there. Professor Aditya, are we audible? Professor Aditya, are we audible? Okay. Sir, I think you can see Anurag Singh, Dr. Anurag Singh's name.
Online participant, can you hear us?
Aditya join once again. Okay.
Online participant.
Professor Aditya, can you hear us? Yes?
And can you speak after unmute so that I can check your voice is appearing or not? Can anyone speak after unmute? The speed of typing?
Yes. We are audible?
So
Okay.
They are not ready to.
Professor Aditya, are you audible? Can you say hi?
Yes, sir, you are audible.
Professor Aditya, are you audible?
Can you call him?
Aditya. Good afternoon, everybody. Please have patience, and I think Dr. Aditya will be joining anytime soon. So,
जी करो तुम पासवर्ड लगाओगे प्रोटेक्टेड धीरे उसको बता Dr. Aditya, are we audible?
Can you listen now?
Yes, Dr.
Finally.
Thank you. We can hear you.
Okay.
Should we start?
Let me share the.
Should we start? A very good afternoon, dear participants. With us, Dr. Aditya Nigam. He is an associate professor and head of the department in the computer and electrical engineering at IIT Mandi. He has received his master's, MTech and PhD degree from Indian Institute of Technology, Kanpur. He is passionate about teaching, and most of his 6 years of teaching, he is actually related to the deep learning and its applications. He covers the concept starting from the basic to the advanced level. He regularly organizes various workshops such as Indian workshop on applied deep learning, Indian workshop on applied machine learning, and similar kind of at various national and international levels. His research interests are in deep learning, biometric, medical image processing, and its analysis. He has published more than 150 research papers in the top international journals and articles. He is two-time recipient of the Teaching Excellence Award at the IIT Mandi, which is a very notable achievement. Thank you, Professor Aditya, for kindly separating the time from your busy schedule. I know that right now you are traveling and it is very difficult for you to manage the time. But despite your busy schedule, you have given us the opportunity to listen you in this time. Thank you for agreeing to deliver the session. Over to you, sir. Can we have a huge round of applause? Thank you. Mr. Aditya.
Am I audible?
Yes, you are. Yes.
I'm audible. The issue is that as Professor already said, as traffic, he said that is it possible. Right now I'm at a very remote location and but I'm not sure that whether you can see my screen.
No, we cannot see your screen.
See that screen?
Your screen is not visible, sir. It is not shared. It is not shared.
Yes, I guess.
Yes, I think now it is coming. Yes, we can see.
But you can see that screen, right?
Yes, we can see. Encoder decoder architecture. Yes, the transformer slide.
Because the issue may be that the network may not be very good. So, but still, I can try. You can see that the architecture and okay, because there is also a feedback which is coming. Okay, now it's muted probably. In between, if you are not able to listen or something, Kamlesh sir has my number, he will try. And if I'm not getting any information, I assume that network is working. So as we all know that we are here to understand large language models. And if I say that large language model, it essentially means that we need to understand basically how these language models actually work. What's the meaning of a language model and how it actually works. And language is mostly being seen as, one can say, language to language translation. If I say language to language translation, means that's one language to other. So you actually have a source language, and from source you want to go to the destination language. The source language is there, the destination language is there. Language and language translation has to be the goal. So language translation was actually being the goal, and in order to manage this language translation, there were so many different types of architectures, models, and other type of machine learning algorithms which were actually being there and then as it all happened that a new model came that essentially been called as a transformer model. So before transformer model, we actually have language-to-language translation, and that can be done using LSTM models. So LSTM models are nothing but we will not be much talking about it, but LSTM is essentially having a memory along with it, and you just remember that what is being shown so far, and I try to remember that what I have seen so far and what's the current input, and it tries to detect or say it tries to predict what's going to be the next input. So that is the way in which LSTM model usually work, but there was a big issue. One can say a difference between transformer and the LSTM, and that was the advantage that we started to get in the case of the transformer is that scalability. So if you have good amount of data, LSTMs are nothing but they are so these LSTM networks are sequential. So if a model is a sequential model, it's nothing, it's going to take, so if I have say x1, if I have x2, if I have x3 and so on and f2, xn, so we used to say that it's a time series. From x1 we can make x2, from x2 we can talk about x3 and so on and so forth. Now if I show you x3 or the thing that I have shown up to x3, somebody has to calculate that what is going to be x4, and that is the time series prediction problem that we used to talk about. And the problem is that it's inherently sequential. I mean, you can't show x5 before x5 can't be shown in time. You first have to show x1, then x2, then x3, then x4, and then only x5 is going to be there. So because of this inherent sequential nature of LSTM sort of networks, they were not very fast to train. Fast to train means that they can train, they can learn, they can understand depending upon the memory that you have and the amount of storage that you have. Depending upon that, you can decide that how much amount of information that you can retain. But the problem was that that because of this sequentiality, you may not be in a position to use all your GPU powers, because x5 or xn can't be shown before x1 to x of n minus 1. You will have to, in fact you will have to wait. You will have to wait for good amount of time. In fact, you will have to wait for xn. You will have to wait for x. If you want to show xn, you will have to wait for nth time step. Before that, you can't see, not show the data, and because of that, it becomes complex or becomes difficult. Yeah. Is it not possible? Is it not
मैडम बात करूं चाहे वो संजय शर्मा हो चाहे अमित कुमार हो सर म्यूट
something has happened. I'm sorry. I mean, how you guys can listen, or anyone who was listening to?
So somebody in between, there was some problem. Please go ahead. Please start. Please go ahead.
Should I continue?
Yes, please.
Yes, please continue.
Okay. Yeah, so the point is that if you have a source language, if you have a destination language, you need to know how can I convert source to destination. LSTM was essentially one such model, but unfortunately it was sequential, because of which you are not in a position to train it fast. And then it comes a transformer model. A transformer says that attention is all what you need, that you will see that what does it mean. But transformer essentially is a network which will take your time series data like x1, x2, x3 and xn and all of them at the same time step, exactly at the same point of time, go inside the network. Inherently sequential time series prediction got completely changed and become parallelizable time series prediction or time series learning problem, and because of which transformers becomes very popular because they are being they can be trained very fast. Inherent parallelization is there. All the tokens, if you have a sentence of 20 words or 50 words or even bigger, 1000 words, all of them can be shown at the same time to the network, and their parallelism can be shared, parallelized, and because of which they can be trained. And they can be trained very fast. And if something can be trained very fast, you can train with a bigger amount of data. So that's the most important thing, that even in the case of transformer paper, they never ever have said that our performance is better than the old LSTM model. They only have claimed that our performance is similar to LSTM, but we can be trained very fast. And if we can be trained very fast, then you can show me huge amount of data. So with this, let's start that whenever you have a language translation part, it is the source language and there's a destination language, and that destination is, suppose that right now maybe French. So I am good has to go in. You have encoder network, you have decoder network, and I am good will first go inside the encoder and you will get 3 tokens. So essentially the token of I, the token of M, the token of good. All of these 3 guys will go at the single shot inside my encoder, and you are going to get how many tokens? Token number 1, token number 2, token number 3. First token for M, third token for good. Once you get these 3 tokens, these token representations somehow being given to the decoder, and decoder has to, in the first step, say that hey, J, West and Y. It will do 3 things. J, West and Y. So it's going to give you 3 predictions. What's that? It is that what is the equivalence of this sentence in the destination language, which is right now being the French language. Now what our purpose is to understand what is this encoder, what is this decoder, and later we will see that how this is being related to LLM. There's a large language model. So with this you can understand that by the way this is a language model. It is able to predict and figure out that what's the language semantic of the source, language semantic of the destination, and how a language can be converted into the destination. So it's essentially have got the all related stuff, all the things related to the language model. Why it is large? And large is not like some MB or GB of data. These models are so scalable, so big that you can train such networks onto all the internet. All the internet they have described and taken, and they have shown all that stuff going into the decoder, going on to the encoder and decoder, and it can learn and take data, assuming it to be all the internet which is being available. Now, such a highly scalable model is the thing which is being called as a transformer, and that is just happening because of its inherently parallelizable architecture. So let us go and understand what is encoder. So encoder, I am good, will go into the encoder and you are going to get a representation. Now this representation is not in for English, not for German or French or whatever in the destination. This representation is going to be a latent representation, and that latent representation is going to be for source and the destination's intermediate part of representation. Representation which is somehow being taken source sentence and convert into some latent representation which is slightly close towards the destination, and later when you are decoding, when you are converting, you use this representation to predict the English, the corresponding destination language representation. So it's essentially having encoder, multiple encoders. We need to see how many encoders, so 10 encoders are going to be there, but what is going to be inside an encoder? So let us see. So you have embedding, you have the positional embedding. So as you all understand that never ever an English word can go inside a network, so you have some input embedding layer. This layer will just take these tokens. So these tokens are I am good. Somebody need to understand that I, then M, then good. These are the three tokens, and the token number 1, token number 2, token number 3. So you have got 3 tokens coming out of that. For each and every token, you have positional embedding. The positional embedding of this token is this token positional embedding is this, and this token positional embedding is this. Now both of these things are finally going to be added. Now why do you need positional embedding? Understand that I am going is a time series sentence. All of this can be shown at the same time, means that there is no meaning of time series. It doesn't depend upon time. This input, but it doesn't depend upon time. It is the same that representation of I and M and good. Now, is it that I am good is equivalent to am I good or good am I or whatever the permutation? No, all permutations are not equivalent. So there has to be someone who try to add the positional information along with these input embeddings so as to make it a meaningful. That is the utility that this is bringing. So here you can see the time. Given that the time series is broken into input embedding as well as the positional inputting. It's being break so that now you can parallelize the thing. Now you can see that I coming here and I coming at 5th time step. Both of these I may have the same input embedding but different output embedding, because of which I coming at 5th location and I coming at 8th location. Both of these are going to have meanings because of this addition. I assume that positional embedding is also okay. Now, when we are going inside, so you have got the feature. How many features? There are 3 things that will be coming out. And these 3 things will go inside this multi-annotation feed forward, and then the final interpretation you are going to get. And by the way, this is the single encoder block. Switch multiple and encoder block 1, encoder block 2, encoder block 3, encoder block 4. Similar to that, you are going to have the decoder block. Decoder block is going to have the same thing. Along with that, it's also going to have one more thing top of it. This is a diagram of our encoder block, which is having an attention head, then layer normalization, then feed forward network, then again the layer normalization. You can see that if your network is deep, the most important thing that you need to do is that to have a residual connection so as to create deeper networks. You all know that ResNet has, and these are going to be the identity or the connections, residual connections which are taking the previous input carried forward after a layer. So this is one thing. The other thing is that similar to the batch normalization, we need to normalize the features which are coming out of every layer. This is multi-annotation. Something goes in, something comes out, and I normalize that set of features. That's called the layer normalization. And then we give it to the feed forward network, and you see that again that we are having the residual connection, and then again we do the layer normalization. So two simple things: residual connection and the layer normalization after each and every component, which will make these systems, even if they are deeper, you can create this. The same thing is going to be there, but in the case of decoder, along with attention, which is initially the self-attention, you also need a cross-attention that I will show you. But in the case of encoder, you only have self-attention, and in the case of decoder, you have self-attention and cross as well as a cross-attention. Now, what is attention? So, attention is that suppose that I am having sentence 1. That is my sentence 1, and these are the tokens like x1 and x2 and x3 and xn. And if you have sentence 2, and similarly you also have all the corresponding tokens. Now if you wanted to know that this guy, so just going to talk about this. Before that, let us one more thing that I wanted to introduce is that suppose that you have a time series. Now this time series, how can you say that there is some semantic? What's the meaning of this time series? What is the semantic meaning of this time series is being represented as how these tokens are interconnected. Let us say that this token is having connection with this token is having connection with this guy is having connection with this guy is having connection here, and so forth. So there is multiple connection. Like here you see that it is having connections with the word is art dog. The word is art dog ate the food because it was hungry. Now this it, who is referring? It is referring to art or dog or ate or the or food or because of what? It is referring to dog. We need to figure out why. Because these connections are going to tell you what is the meaning, what is the semantic, how these words are related to each other. And if we can get that, we can somehow understand that even if it is talking about dog, and you may use why, or because it has eaten something, so he was hungry. Who has eaten? It has to be representation, has to be close to dog because it is related to dog and so forth. What dog has eaten? Dog has eaten the food. So these connections somehow need to be learned. How one can learn such connection is the thing that we are right now looking for. Now suppose that our point is that I wanted to know something about the third token. Then third token has to be compared with the first one, the second, the third, the fourth, the fifth and sixth. How can I compare two tokens? The token number 1 or any token I is nothing but a vector because it's an embedding. Now if I have two embeddings, basically two vectors, how close or far they? Just do the dot product. Two vector dot products the cosine similarity and you just find out how close these two words are. Now, what will happen is that in the case of x3, so as to know that the relationship of x3 with all of them one by one. Okay. How can we do that? We understand that we can take the both of their representation and just find out their cosine similarity. But then we understand that no, it is it is one way to do the addition, and it was been done before transformer networks. Later, transformer said that let us do it in a different way. When a person, when a token wanted to figure out its resemblance with everyone, it has to query. A token is going to query. Let's see. I am looking for all of you who are similar to me. This token will say that I am looking for tokens who are similar to me. Tokens similar to x3. We are looking for tokens which are similar to x3. How can I get those tokens which are similar to x3? So x3, let me write something. x3. So x3 is query and x1 to xn. All of them has to respond to this query. What is going to happen here is that any token xi is being converted into its key form, and value form. So whenever xi needs to query, its query form is going to be used. When xi is going to respond to someone else's query, its key value has to be used, and using the query and the key values, we are going to get the attention. That this attention is going to be used so as to tell the final representation, and that is being done using the value that you will see in a moment. So what's going to happen? That if here it wanted to know its resemblance with everyone else, it has to, so it query value, and all of these guys, they are going to give their key value. So all this dot product is going to be computed, and like this you can see that suppose that this is the word and that's the representation, its query will be there, Q will be there, and value will be there. These are the three matrices, and all these matrices are going to be used to convert all of them into their key representation. So first words is going to be the key representation, the query representation, the value representation. Now what's going to happen? That the key and the queries are going to be multiplied. As I have said that its multiplication is just a dot product, and if you wanted to know that suppose that this is your it, then its query will be taken and all others keys are going to be used and the values are being placed over here. So this is the dot product of its query multiplied by first words key, second words key, second word, third words key, fourth word key, and so on. So its query is going to be multiplied with all the other words key values, and the value that you are going to get is the dot product, and this dot product, if it is high, it's going to represent that those words are having high connection with it and other words are having less connection with it, and over that we apply the self-production. So over that we apply the softmax in this direction, and you will get the some values will be high and some values will be low. So as you can see here in this example, it is going to have a high relationship with dogs representation and low relation with others representation, and so on and so forth. So once you have got these attentions, and these attentions are somehow going to be described, suppose that 0.3, 0.1, 0.01 or so forth, and maybe some place you will get 0.6, very high relationship. Maybe that's the dog. So what is going to be the final? So this is the initial representation of it. This is the initial representation of it. This is the initial representation of all the words. But after first round of self-attention computation, this is the bullet going to be the final representation of it, which was this. Now got converted into this. And what is that? It is going to be the values of all these words are attention between the two. It means that new representation of it is going to be coming from all the words representation. It the value of all these words are going to be multiplied by the attention that you have got. And how you have got the attention? Query of this got multiplied by the keys of all of them, and you will get the value 1, value 2. These are the attention values, attention 1, attention 2, attention 3, and imperatively you can see that the attention of it will be high. So the value of dog is being multiplied by the attention A2, and A2 will be high. So most of the weight is being given to those representations which are having high correlation or connection with a given word. So in this way you can see that the very simple thing which has happened, and how it has happened is that the previous representations got converted into a new representation, and these representations are slightly defined on the better representation as well as the previous one. The only thing is that if first sentence is S1 and the other sentence is also S1, same in the case where I have shown you. If both of these sentences are same, this is called as self-attention. Otherwise, it will be, if both of these word sentences are different, it will be called as cross-attention. This is self-attention, example, and if both of them are different, suppose that here its language is English and here the language is Hindi, then, and if you wanted to still know that what is the relation, I am going मैं जाना चाहता हूँ. So मैं is going to have a high relationship with this. But how you are going to get this? For this you need to use the cross attention. So that's the major difference between cross attention and self attention. And just now I am going to show you in terms of images that I am doing and X1, X2 and X3, and this is the input embedding of I, then the input embedding of M, and the input embedding of good. So these are the three embeddings that we have got. All of these embeddings are going to be of 512 dimensions. Now you see that all these input embeddings, embedding this and this and this, they are converted into their query, key and matrix form. How? We have got matrix 1, matrix 2, matrix 3. So we have got three matrices. As I have said, they have to be properly learned and they need to be learned in a way so that what final representation that we are going to get after self-attention, it has to be good enough. So these matrices are going to be learned. And this is the representation of my x1. This is the query representation of my x1. This is the key representation of my x1. And this is the value representation of my x1. In order to understand why you need query, key and value, just think about that. I suppose that you are the data. Some student is the data. This is data D. Now you see that how you behave when you go and ask for money. Suppose that you want 10,000 rupees. You go and ask with someone. So the way you are going to ask, that is your query representation. The same D1, when somebody comes to you and you respond to that request that I need 10,000 rupees, how you respond? You respond with your key version. And there is another your representation D1, that is the value representation. So that is the flexibility that's been provided to each and every word so as to have the best possible expressibility. So each and every word can have its query representation, key representation and value representation. Whenever that word wants its own relationship with other words, it has to come with its query and others are going to come with their keys. Now you see that query and key, both of them got multiplied and you are going to get I and I. Their relationship Q1, K1. I and M, Q1, K2. I and good, Q1, K3. Diagonals are going to be the word corresponding to its own set. M and M. And M and M, that's Q2, K2. And then this is what you have got somehow, that I related to I is this, I related to M is this, I related to good is this, and then I apply a softmax onto that, which says that this is having high relationship with this, second highest one is this, and the lowest one is this. It's going to be like this. That's being done over time. Certain things I have to skip because of the time, so we will somehow try to understand how on broad level it's happening. You see that that's going to be the soft connection, and anyways it's going to be normalized. These numbers can be big depending upon the dimensionality, so it has to be properly normalized. So it's been normalized using the dimensionality under the program. So this is after softmax. You see that I is having very high relationship with this guy and no relationship with other. Now how you are going to get the representation of first level representation of I is this, the initial representation that I have shown was this. This was the initial representation. After that we have got the query key and value representation. Using that, how can I get the next level representation of I is, this is the attention. And I take the initial representation of I got multiplied with I's representation is a vector. I take that vector multiplied by 0.9. I take the vector representation of M, initial vector representation of M multiplied with this, and the initial representation of 2 and multiplied with this, and then add all three, and you are going to get the output. So here what's going to happen is that this is the initial representation, this is the query, this is the key, this is the value. these are the attentions, and the value of I is multiplied by 0.9, the value of M is multiplied by 0.7, the value of 2 is multiplied by 0.03. And once you have multiplied, so what's going to happen that these two values are now going to be multiplied. This is the attention which is going to be multiplied by the value. So attention multiplied by the value is this. So what's going to happen that this vector is the representation, that's the value of I, value of M, value of good, and you take these values and multiply corresponding to these weights, and when they are aggregated, the values of I, M and good are aggregated in this way, you are going to get the final representation of I. Similarly, the final representation of M and good can also be computed the way I have shown, that Z1 is the representation of the first word, in which this representation, the value of the first word got multiplied by the attention. The value of M is going to be multiplied, this is the value or the vector for M, going to be multiplied by this and so forth, and then you add. So essentially what has happened in self-attention is nothing but the query and the key got multiplied, then scaled by their internal curve decay or the dimensionality, and then softmax has been applied, so now you have got the attention, and these attentions are being multiplied by the value, and finally you get Z1 or any word final representation, and then you can concatenate all these representations. So, oh, by the way, how you have got multiple representation of the same, but because here what has happened, here you have got one representation and the one final representation for each word. What does it mean? That you have x1 to xn, and then you have got z1 to zn, and these are the representations for each of them. But these z1s are different. That is multi-head, I am going to talk about that. But before that, for each and every word which is going in, corresponding x1 to xn, you will get, suppose that y1 to yn, this is going to be the final representation of each and every input word. But in order to get them right or having much more expressibility, instead of applying one self-attention head, we apply multiple self-attention heads. So what are those multiple self-attention and what does it mean? So one head means one pair of query, key and value vectors. You have one query, key and value vectors. Now, just think about that there is a word. Now think about anyone. I mean, right now in the audience, I only know Kamlesh sir. So I will see that Kamlesh Tiwari as a data. Now Kamlesh Tiwari as a data is x1. And do you think that the relationship of this x1 with every other one is always fixed on one type of relationship? No, his behavior, his relationship with each and every word is, depends upon the context. The way he talks to me is different. The way in which he is going to talk to you is different. The way in which he is going to talk with his son is going to be different. And the way in which he is going to talk to his wife, it is going to be different. So, each and every word, depending upon the context, like Sachin pilot, now Sachin and pilot. Now Sachin Tendulkar, Sachin word is one thing. The pilot, so pilot doesn't mean that the surname or he is actually a pilot. Similarly, Python can also be referred as his name as well as referred to a language. It depends upon the context. But how can I give such expressibility to a word? By the way, this can only be done using multiple heads. So instead of converting x1 by one head like this, we can have multiple heads. So I have head 1, I have head 2, I have head 3, I have head 8, and same data after head 1 is going to be head 1. Head 2 is going to be this, head 3 is going to be this, and head 8 is going to be this. And then I concatenate all of them, and all of them got concatenated. And finally, I will get a much more enriched final single Z I or Z1 representation that I or Z1 representation for my X, I or X1 degree. As I said, the positive embedding has to be added. It's slightly complex, so I need to leave and just give a layer normalization as I have said that it's going to be there. Feed forward neural network, as I have said that there are two components in our network. First one was encoder, the other one was decoder. This is multi-head attention. This is the layer normalization, then it's the feed forward. So we have seen this multi-head attention in which there is multiple heads, and all of these heads are going to be used and utilized. Later you do layer normalization, and then you do feed forward. So always understand the feed forward neural networks are there so as to convert and once more transform or learn a transformation function that can take our input data and convert it into a much more meaningful way. So that's why one more feed forward layer is being applied. And slightly fast because given amount of time is it may be difficult. So now you can see that input is going, then multi-head attention, then add NOR. What's that? Add NOR is that addition of this, that's our skip connect or residual connections. What is NOR? That's the layer. And then I do feed forward network, the feed forward will go and then add NOR. What does it mean? That's again the residual connection and layer normalization. So you have multi-head attention, you have feed forward, and both of them are connected by add NOR layer. The final encoder can actually be seen as that you have input embedding, you have position embedding, you have multi-head attention, you have add NOR, you have feed forward, you have add NOR, and if this is one encoder, in this way you are having n such encoder. And this n can be 8 or 10 or 15 or 20 depending on the amount of memory that you have. RAM. Now, the decoder is also going to have a very similar type of structure, but before that, you just see that that's the tokens, that's the positional embedding, and when I add both of them, it passes on to too many encoders, and you have got the final encoder representation, and this final encoder representation is being given to every decoder block. Decoder is also having very similar type of structure like the way I have talked about encoder block, but along with sun potential, it is also having the cross attention. That's the only thing, and it's being trained in auto-regressive manner. What does it mean? Just you think that that the input is how are you doing, because now it's a question answer thing. The example, how are you doing? The answer is I am good at some more things, but suppose that it's been trained, then it has to see that I start of the sentence that I am good at. It has seen so far. Network has to print what is going to be the next. Now that is going to be the auto-regressive training, that you have the sentence and you have its corresponding output, and then its output has to be predicted one word. First word, then you see first word and the output of the encoder and the word that I have seen so far. Both of this you have seen, this you have seen, using both of them. Both of these things will go up, and at last here we are going to predict what is going to be the next token. How it's been shown, I am going to show it again, that our example coming back to the language translation model, that I am good, then it will go I am good. You have got I am good latent representations. These latent representations along with the French equivalent shown one by one, and it has to predict to me that what's going to be the first one, the second one, the third one, the fourth one. How? So you have got the latent representation. These latent representations are being given to the decoder, and first the decoder is being shown as SO, as start of the sentence. So it will say that the start of the sentence as well as what I have seen in English using both of them. Decoder need to predict what is going to be the next word, and so on and so on and so on, and it has to finally tell that the next word is J. After that, what will happen? That S, O, S, and J. Both of these things are being shown to the decoder and the previous representations, and it has to predict that what is going to be the next word was. And then J, where all these things are being shown at once, and it has to use the things in the English that's been seen so far, and using all of them, it has to predict that what is going to be the next word that comes. In this way, you can see that it's going to be trained in an auto-regressive way. And since you know that what's the ground truth, you can use always that what is the corresponding prediction and its corresponding ground truth and find out the loss and train this network as well as this network in such a way so as to get our auto-regressive model being trained in this way. The same thing is also happening that output embedding. You can see that the source language comes over here, the destination is coming over here, and you have the output embedding layer as well as the position embedding, because you can understand that the code is also going to use the same language. But here one more thing is that I have not told you is that thing over here. So you can see that that is my encoder. You write it down. That's my encoder. That is my decoder. Encoder is having multi-head and knob, feed forward and knob. This is having multi-head and knob, multi-head and knob, feed forward and knob. So it's having two multi-attention. Now the point is that first attention head is for self-attention, which is going to learn the semantic of the destination language. Here, this guy has learned the semantic of source language. This will learn the semantic of destination language. This guy is going to learn the cross attention. Cross attention means that suppose that this was I am going, and this is my jana up to this. Now next word has to be treated as chahata. So my jana will go in. Here you will get the relationship of my and jana only up to this. Because other words we can't see because we are going to predict that word. So I am going to predict that word. So that because of that, self-attention is only being done on masked data. Masked destination data. So if I say that मैं जाना, next word has to be something that I need to predict. So I should not be showing that word to my network. So मैं जाना dash that's the mask. Self-attention is going to be computed. But in the case of cross attention, I am going to use मैं and jana, and both of these things has to be attended by the things that I have seen so far in my English name. मैं जाना and चाहता. So चाहता, before that to predict that what is this word, I need to compute the cross attention. The cross attention between who? Cross attention has to be computed between मैं जाना and I have seen things so far over here. So the key and the values are going to be coming over here, and query will be coming from here. Because as you know that मैं wanted to know I am connected to whom. मैं जानना चाहता है मैं यहाँ पे किनके साथ कैसे कनेक्टेड हूँ. Similarly जाना जानना चाहता है कि मैं यहाँ पे किनके साथ कनेक्टेड हूँ. So both of these words, their query is going to be there, and the key and the value is going to be coming from the encoded representation of the source language. And that's the major difference between that self-attention here is being computed, but it is not the masked self-attention. Self-attention computed in the encoder is not the masked self-attention, that is the full self-attention. Here you again compute the self-attention. This self-attention is for the source line are going to predict the next word, and this guy is going to compute the cross attention. Cross attention has to be computed between English latent representation and destination representation that we have seen so far, but query is being coming from the destination, and destination level source is being coming from the sources, and the key and the value is being coming from the source. Finally, you get the final representation, and then you apply software and also probabilities and so on and so forth, so as to get the next word. The way that I have shown, that's going to be obtained in the auto regressive method. Anyway, my time is up because I assume that it's up to Kamlesh sir can tell me that can I take 3-4 minutes, because in that I can try to explain what bird and
Yes, please continue. Whatever time you wish.
okay. So once we understand this, and this network is being become a benchmark and
Meanwhile, I just Aditya sir, just in case any of the participant have any questions, you can ask. Is it fine?
Any question?
Yeah. Do you have any questions? Online participants? Can you type yes that you are able to hear and that you are able to follow? On the chat, can you please type yes? Everybody, online participants, can you type yes? Nobody is typing.
Okay.
Okay. I think Aditya sir, you can continue.
Yeah. So very quickly I will tell you that now what happened is that transformer started to be trained and started to produce very good results and so on. And by the way, as I have said that they are being trained in an auto-regressive manner in which you just predict what's going to be the next word in the destination language, and you got a loss over here, and that loss is being back propagated like this, and it's being trained. Now what happened is that they understand that both are these representations and these networks, encoder and decoder, they are very versatile. So they break over here. And the encoder becomes burned. And the decoder becomes GPT. The GPT is the generative pre-training thing, and burned is the bidirectional encoder only representation. Bidirectional encoder and representation. So now you can see that this is burned. It's an encoder only. I mean, words are going in, words and their representations are coming out. That's plain, that's the bird. You have encoders, multiple encoders. Along with these words, you also introduce one token that is called as the CLS. CLS token is the classification token. This token is embedded as a token which understands how to classify a sentence. Now suppose that you have got certain sentences in some reviews of a movie, and then you want to classify them into good or a bad. Then you have a CLS token, and the CLS token is being embedded, and now you have got, suppose that your review is of say 500, and suppose that your review is having 20 words. Then your representation is also having first token as CLS and then 20 words corresponding token. All of them will go inside this encoder, and it is going to predict the token for CLS as well as for every other words token. And then this keep on refining after each and every encoder. That final layer, you will get again all inputs corresponding to that output tokens. You just take the classification token and train our classifier onto that. We just have a fully connected network and a regress onto that, and finally get the cross entropy loss, which means the number of losses that you have. Same thing, you can see that these are the residual connections, we said that, so encoder 1, encoder 2, and so on and so forth. So the point here is that they can train mini bird, they can train tiny bird, mini bird, small bird, and medium bird. So tiny bird can have 2 encoders, 3 encoders, and bigger networks can have 8 to 10. By the way, these networks are going to have huge amount and very big amount of parameters, so that you can't have because the cell potential is very big. Cell potential takes huge amount of parameters and a lot of communication to be computed as a matrix multiplication. Several times these matrices are very big, so as to learn. So depending upon that, depending upon the amount of memory that you have, you can train this network. So you can train it in this way, that what's the classification, or but there are certain interesting pre-training strategy. First one was masked language prediction, and next one is the next sentence prediction. In 2 to 3 minutes, I just explain them and we are progressing. So the masked language prediction is that you take the whole sentence. I have a CLS token, that's okay. You take the full sentence and you randomly mask 15% of the token. I mask this and this and this and this, certain 15% tokens, and let my network predict that what was those masked. It was something over here, something over here, something over here. I know that what is its corresponding token, that is why I just mask them and ask my network to predict them. My network try to predict what was being there. So once you find out that what was being there, you find out that what has to be there, the ground truth, and compute loss 1, loss 2, loss 3 for all the 15% tokens, add all of them and then propagate it. That is masked language prediction. This is not trained for any classification so far, not a predefined or a fixed task. This is a generic type of training which is happening, which is just trying to learn what are the tokens which are essentially going to be masked. Or the tokens which are being masked. If I know that the tokens which are being masked, I actually understand that what is how can I read and predict about the sentence. The other thing is the next sentence prediction, in which you have sentence 1 and you have sentence 2. Separated by a separating token. You have CLS token, you have certain tokens. You have sentence 1 token, you have sentence 2 token, and then you have separator in between. Within first sentence, you have certain tokens which are masked. Within second token, you have certain tokens which are masked. And next language prediction, next sentence prediction is going to say that just you need to train it as a classification task, that whether the sentence 1 and sentence 2 they are co-occurring, which means that sentence 1 preceding sentence 2, is it true or false? If it is true or false, then depending upon that you train. So now you can see that positional embeddings are there, segment embeddings are there, because these are maybe the tokens for the first segment. This is going to be the token for the second segment. This is the classification token, and this is the first sentence and the separator token embedding, the second sentence and the separator. You add all of them, and that's becoming your input. You show it to your encoder, encoder keep on working on to that. Finally, you are going to get the classification. Depending upon that, you got a loss, and trade that for the next sentence prediction or MLM, like the next basically the masked language prediction. So now you see that you first pre-train, because for a particular task or the downstream task that you want to work on, you are not going to have that much amount of data. So what instead we do, that we take huge amount of data irrespective of the task, we train it as a masked language prediction as well as the next sentence prediction, and then using both of them, once we are trained and we have got good results or initial training has been done, we fine tune our network depending upon our final output task. Sorry, I have taken more minutes. I am done with this. And if you have any questions, please ask.
Sir?
Otherwise, I am done.
Sir? Sir, I have one question from encoder decoder.
Loud.
Sir, what is exactly the purpose of positional encoding?
Yeah, the exact purpose of positional encoding is that whenever matrix multiplication is going to happen, because transformer I don't know, I am getting a feedback. I request that it can be muted. I just answer the question. Yeah. The point is that positional embeddings are there. The reason of using positional embedding is that transformers are both, matrix multiplications are positional invariant. I mean, you take a matrix and just replace its first row with the second row. Just swap them. It's not going to, make any difference. But the point is that when I say x1, x2, x3, they can come at once, at any point of time. All these x1, x2, x3, they are coming. and they are being shown to the network at the same time, then the time information is being lost. And if time information is being lost, time series no longer become the time series. That's the advantage as well as the disadvantage of transformer. The advantage is that now it's the the other thing is that since time information is being lost, you just can't see that data is no more a time series data. I am going and am I going, they are not same. So how can I make am I going and I am going to be a two different things? Is that I just take their input embedding and add the positional embedding. Positional embedding is nothing but for every location it is fixed. It's the fixed embedding, which is not a learnable embedding, and for every position it is fixed. The first location, this is the embedding, 512 dimensional encoding for first word, the second word, the third word, and the fourth word. You take any word and its location, and the token embedding is being computed by the token embedding there, and positional embedding is directly computing as dependent upon the location, and you add it. Anyone else?
Yes, sir, I have one more question. Am I audible to you?
Yes. You can
Yeah,
ask.
so can we use LLMs to generate synthetic data sets? Like, for example, if we have an application supposed to estimate soil parameters. So, what would be the drawbacks in those cases? And also, one more question. I have learned about few methods where reinforcement learning through human feedbacks were used to fine-tune LLMs. Can you throw some light as how they work?
Yes. So as you have said that the point is you are having two questions. The first question is that the soil and other restriction. If you have the time series data for it and understand that if you have very small amount of data, then LSTMs are good enough. And even if you have a very small amount of data, then statistical methods are there, Riemann, other model. But if you have substantial amount of data, but not too big, then RN and LSTM models can be workable. But if you have huge amount of data and LSTMs and other models not in a position to learn such complex time series, you can go with you can go with transformer. This is the first thing. And data is there. These are data hungry models. They can eat and do the things for you. The only thing is that you need to have good amount of data. And you just first pre-train your model like certain strategies as I have said. But the other thing is that reinforcement learning got reinforcement human feedback sort of learning. That is happening when we train over the other model, that's the ChatGPT model, or the GPT model, as I have said, the generative pre-training model that is being trained in an auto-regressive way. So what they have done is that they have human annotators, and that's a very costly affair. So they have employed so many human annotators to see all this data and manually annotate, and then they have come up with a reward system which is going to say that first your network has to predict something, and then I need to say that how good or bad that output is with respect to a particular human annotator. So GPTs are being trained for question answering tasks. You have a question and you have an answer. But then they said that how good a match is. So they have said that human annotators are also there, and with respect to that human annotator, the output which is coming from your network, how good or bad it is, depending upon that they have defined the reward function. And then they have made a reinforcement learning engine to be trained in such a way so as to maximize that reward, so as to learn always or most of the time that predictions has to be as close as to the human annotators. So that's been trained in that way. But usually you require huge amount of data for that, and those annotations are also not being available.
Okay, sir, thank you.
Sir, I have Yes, sir. So one question that I have here is that while you were explaining self-attention to us, so is self-attention like gathering the importance of the subject or nouns in that sentence? Like, let's suppose we have a sentence like the dog ran after the cat. So we have subjects here as dog and other things. So are we trying to find the importance of dog in this particular sentence, or is the self-attention something like this, or is it like different?
Yeah, thank you. So the point is that self-attention essentially tries to learn the semantic within the language. Within the language, suppose that you have an English and you have another sentence in English, and both of these sentences, if they are exactly same, then you can learn that what is the relationship, that who ate the food, who was hungry. So all these connections are going to tell that dog ate the food, dog was hungry, and so on and so forth. So self-attention tries to learn the semantic within the sentence. Across the sentence, if you wanted to see, across like S1 and S2, both of them are different, then it becomes cross-attention. In the case of cross-attention, S1 and S2 can be in English, but both of them can be two different sentences. If they are two different sentences, you suppose that you wanted to summarize something, that I want to go because I was not happy and something has happened and so on and so forth. And the summarization is that that guy did arrive on to that event. Now, given these two sentences, both of them are English, but one is the extended sentence and the other one is a summary. So, in that case, you can again compute the attention, but this attention is going to be self-attention, but being seen as the cross-attention, because there's not the attention between the two same things. So, as you have said, self-attentions are being crafted, designed in such a way so as to learn the dependence within the sentence.
Sir, is it like within the sentence or like, sir, is it like within the sentence, or is it like if I send an input paragraph, then within all those sentences I would try to find the relation between any subject or adjective, something like that. Like in one input, is it all for all the things, like all the importance with respect to each other? And if I'm comparing it to another input, then it becomes cross attention. Or is it only for inside a sentence?
It is only for the inside the sentence, for the self-attention. It is going to be that, suppose that your paragraph is there, and your paragraph is having 512 different tokens. And you take that paragraph, so it will become 512 cross 512 dimensional matrix for the attention, in which each and every word within that paragraph is going to be compared with each and every word within that paragraph. So that is self-attention, and each and every word is going to be compared with each and every other or the same word itself. So its query is coming and other's key is coming, and that is going to be that the word compared with each and every word within that sentence or the paragraph, whatever be your input token length. So depending upon that, self-attention will work, and which is essentially trying to figure out that what's the relationship of a word within that paragraph. Is that fine?
Yes, sir.
Still not clear?
Yes, sir. Yes, sir. So one more question, different
Yeah.
to this, that is it possible?
Before that, one thing that I wanted to say, that I was really very fast, as well as I am somewhere out, so and was not in the proper frame in which I can do everything, family and everyone is in the same room. But I somehow tried to manage. Still, if you guys feel that all the things are not clearly covered, I can tell you that go on to YouTube. There is my channel. Write Deep Learning at IIT Mandi, and you enter. You are going to get my full channel. In that transformer playlist is there. 4.5 hours I was teaching for transformer in the single stretch. You can read things from there. Kamlesh sir can also share that link as well. You just have to write Deep Learning at IIT Mandi on YouTube. You are going to get a full playlist of 4.5 hours of transformer. And I'm 100% sure that all of you can understand each and everything. What is position embedding? Why do you need position embedding? Why masking has been done in decoder? Why masking is not being done in an encoder? What is attention? What is self-attention? Why soft attention? Why under root decay is going to be divided? What is layer normalization? What were the pros and cons of LSTMs and so on? understood. I covered most of the things, but in a very fast way. Now you can ask the question.
Yes, sir. So the question was, I will definitely look at the videos there. But the question was that, is it possible to make a transformer architecture flexible enough that it can take images as an input and the text as input and get trained on that and get the relation between that? Or maybe voice or video, something like that.
The beauty of transformer network is that it can allow you multimodality. And the next paper is nothing but VIT. That's the visual transformer, visual image transformer. So the way in which we have divided the text, you take the image and divide it into multiple parts and show it to a small CNN network, which will convert each and every this part or the small block of my image and convert it into a vector. Now given this vector, you pass it to the transformer network and everything remains to be the same. Because of that, VIT, and then you can divide it. You have got a video, then that's a VIPIT, video vision transformer. It will take the video and just cut it like a Rubik cube sort of stuff. And each and every cube is being shown to a 3D neural network or something, and you will get the fixed dimensional encoding. So now you see that even if you have text, you can divide it into token. You have image, you divide it into token. You have video, you divide it into token. You have EEG, you divide it into token. If you have speech, you divide it into tokens. So you have multiple dimensionality. You just try to understand how to divide them into meaningful tokens and get features extracted out of that. And the same type of transformer model can work onto all. That's multi-model, LLMs and multi-model transformer models.
So sir, as long as all the data values are being converted into meaningful tokens, be it text, be it image, video, audio, anything like that, as long as it is a meaningful token, we can train a single architecture on all of those data. Is that what you're saying? Like we don't need to, revise the architecture or integrate a different architecture to handle that task.
Yes, correct. And the only thing will be changing is that when you a token, within that token or within that modality, that you take the image token and find out its relationship with all the image token, it will be self-potential. You take the image token and want to find out its relationship with some text token, it will be a cross potential.
Okay, so can you share the title of the paper? So can you share the title of the paper or something like that, link with?
You just write VIT.
VIT.
Vision transformer. VIT and VIPIT. Video vision transformer.
Okay, sir. Thank you, sir. Yes, thank you, sir.
Thank you, Dr. Ashutosh. Sorry, thank you, Dr. Aditya. So nowadays, Aditya was very near to me and stayed with. So I just wanted to tell the online participants, if you have any questions, you can unmute yourself and ask please. I think we can take one question only. I think you are typing the question. Can you just unmute yourself and ask the question if you wish the answer?
I didn't have seen any question. I mean, I may not be able to listen to the question. If somebody is asking something, then please ask. I will answer.
The question is what is the key difference in a normal transformer and BERT architecture?
But so the normal transformer is having encoder and decoder and is being trained as auto encoder decoder architecture trained in an auto regressive way. But is only encoder part. So they are also being called as the encoder only architecture. So instead of having the proper decoder, you just take the initial part, only encoder. Tokens are going in, tokens are coming out, and you just But next sentence prediction as well as laws of the language prediction. That I have shown, that is the bidirectional representation, bidirectional encoder representation, that is being the word. That's the main difference. Transformer is having encoder decoder as well, BERT is only having the encoder part of the transformer.
Thank you, Dr. Aditya. And I think we are done with the questions. So thank you very much for your time. And it is really wonderful having you on this session. And you explained everything with a very detailed manner. And even if in the short span of time everybody was able to grasp that what was the technical content, why the things are actually needed to be multiplied, etc. In this mathematical detail, I think everybody is able to follow. Thank you very much for your time. Everybody, we can be. We are saying, say, thank you.
Thank you, Aditya.
Thank you, Aditya.
I request Commissioner, I request you to please share the that my lecture series of transformers. So if they are having doubt,
Yes. Yes. Thank you. I think we can see you also.
Thank you.
Can we take a picture of yours with us? Just.
You just see that the pain which I have rented at the hotel. So, very restaurant.
कोई फोटो कैप्चर से ले लो।
आदित्य सर थोड़ा कैमरा ऊपर करेंगे क्या? हाँ
Like ऊपर ही ऐसे।
Yes. The student can.
उधर से लो ना, नीचे से।
Thank you, Aditya. It was wonderful having you.
Thank you very much. Bye.
Thank you. Yes. Thank you, Aditya. Thank you. Thank you, everybody. We can now close this. Thank you, everybody. Now we can close the session for today. See you tomorrow.